Electromagnetic waves is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. And we're going to start this lesson off talking about Maxwell's equations, who kind of joined electricity and magnetism into a common theory of electromagnetism and predicted the existence of what we now call electromagnetic waves before they were even discovered. We'll talk about how electromagnetic waves are generated. We'll talk about their properties, including like the characteristic frequency and wavelength associated with them, as well as their characteristic speed of propagation. We'll talk about the relationship between intensity and power as they spread out as spherical waves in the same way sound did. And then we'll talk about the Doppler effect and how it applies to electromagnetic waves as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we'll start by talking about Maxwell's equations. And again, he was kind of unifying electricity and magnetism into electromagnetism. He was building upon others' works. And really his four equations are really Gauss's law, which if you recall dealt with electric flux, Gauss's law for magnetism, which deals with magnetic flux. So Faraday's laws and Lenz's laws, which talks about induced EMFs as a result of a changing magnetic flux. And then finally Ampere's law, which we kind of got a special application of Ampere's law for generating a magnetic field due to a current carrying wire. And it turns out that's not the general form of Ampere's law, but the specific one that we kind of studied in this course. And it turns out he really kind of added an extra element to Ampere's law, and so some people call his version the Ampere-Maxwell law as well. Now, the equations themselves are not the important part. The important part is kind of what we derive from them. And so if we take a look at Gauss's law for electric flux, he said for an enclosed surface, so the net electric flux is going to equal the amount of charge that's enclosed divided by epsilon naught. So it's totally dependent upon having enclosed charge. And the idea is that it is possible to have enclosed charge because positive and negative charges exist independently. And so another way to look at this is that we can draw field lines, and those field lines are always going to originate from one of the electric monopoles, the positive charges, and terminate on the other possible electric monopole, the negative charge. And so that's what we really want to take away from this. And yes, it is Gauss's law, but here's kind of what it means. And it's easier to see what it means when we compare it to the second of Maxwell's equations, so Gauss's law for magnetism. And here, the net magnetic flux for any enclosed surface is zero, period. Well, why is that? Well, it turns out with electric fields, you can have positive and negative charges. So with magnetic fields, the bar magnets and stuff like that always come with a north and south pole. If I cut the bar magnet in half, each new piece will have a north and a south pole. And so you can't have a north monopole or just a south monopole separate from each other. If you could, you might be able to draw magnetic field lines from one to the other. But in this case, magnetic field lines always operate in loops and travel right through the magnet and stuff like this. And so they don't really originate or terminate anywhere. They just travel in loops. And the idea is that if you put a bar magnet in an enclosed surface, any electric field line that leaves that surface has to come back through as part of that loop. And so there's no net magnetic flux in an enclosed surface. All right, third one is Faraday's law and Lenz's law for induced EMFs. And recall we said if you have a changing magnetic flux over time, you will induce an EMF. Well, in this case, we can expand a little further and limit it a little further as well. Well, he didn't look at changing magnetic fluxes. He just looked at changing or varying magnetic fields. And he said a varying magnetic field induces an EMF and an electric field. Well, if you're inducing an electric field, that's causing the EMF, so to speak. And so what his big contribution, though, was the fourth part, which we now kind of refer to as Ampere's law. And so he thought nature was symmetrical. And so if a varying magnetic field can induce an electric field, he thought a varying electric field could induce a magnetic field, and he was right. Now, this is not Ampere's law. This is a special application of Ampere's law and the simplified kind of algebraic version of it applied to a long straight wire. And this is the magnetic field strength going around that wire, so to speak. And it's due to a current. Now, in the case here, he thought that this varying electric field that causes a magnetic field was either caused by moving charges or like current in a wire, which really is moving charges. And so he kind of looked at that special application with Ampere's law and kind of modified it for some extra things that Ampere didn't take into account. And so his extra is actually called the Ampere-Maxwell law, not something you need to know. But the big thing here is that you might just summarize this as electric field lines travel from positive to negative. So magnetic field lines travel in loops. So Faraday's law says that a varying magnetic field induces an electric field, and then finally Ampere's law that a varying electric field induces a magnetic field. And it was on the heels of all these that he kind of unified electricity and magnetism, and then also took it a step further and predicted the existence of electromagnetic waves. And he even was able to calculate that they should have a speed of 3.0 times 10 to the 8th meters per second, the speed of light, which is just kind of shocking in retrospect that he predicted this before electromagnetic waves had even been discovered. But the idea was that if you have a changing electric field, well, that's going to generate a magnetic field. In fact, it's going to generate a changing magnetic field. But the changing magnetic field would also generate the changing electric field. And they just reinforce each other and just propagate out into space, so to speak, because they're changing the whole time and they're just kind of generating or inducing each other the whole way down the road. And he was actually able to take some of the earlier works and actually, again, calculate that speed of light as 3.0 times 10 to the 8th meters per second. All right, so from here we are now going to study some of the properties as well as kind of where electromagnetic waves come from. So let's next talk about where electromagnetic waves come from. How are they generated? And simply put, if you have accelerating charge, you're going to have energy being dissipated in the form of these electromagnetic waves. And also simply put, if you have an AC circuit, you have accelerating charges and it is going to generate electromagnetic waves. Let's take a look and see why. So here we've got a simple AC generator hooked up to two conducting rods, one on either side, 180 degrees out of phase. And we're going to kind of follow the electrons as they're kind of sloshed back and forth, if you will, so with the alternating current. And so at one point in time, we might have a buildup of positive charges at one end and therefore negative charges at the other end. And as a result, we're going to have an electric field that points up. And so as the current alternates and shifts the other direction, if you will, so all of a sudden now we'll get to a point where there's no separation of charges. So, and then move a little further down the chain, down the line in time, and you might get a buildup of positive charges at the opposite end and negative, therefore, at the top end. And if you kind of take a look, we've gone from an electric field that pointed straight up at a maximum to no overall electric field, and now to an electric field that points straight down. And if you kind of look at what's going on here, you can see it alternating in strength in such fashion. So in addition, because you have current effectively generated, you got moving charges generated, you can kind of see based on the direction that they're moving and stuff like that, that you're either going to generate a magnetic field going around this way or around this way. And so that's going to alternate though, depending on which way those, technically electrons, but which way the current kind of induced in these rods is moving as well. And we can see that everywhere you see where the electric field is kind of in the plane of the board. So if whether you're going this way or whether you're going this way with the magnetic field, at those same positions, it's either going to point into the board or it's going to point out of the board, and it's going to be in the perpendicular plane. And we'll find out that if you look at that magnetic field, it's going to be perfectly in phase with the electric field, and they'd reinforce one another and kind of continue on and propagate at the speed of light. So let's start off by talking about what an electromagnetic wave exactly is. Now, they are transverse waves where you have an electric field and a magnetic field that are both oscillating. So we've got an electric field that's oscillating. And then a magnetic field that's oscillating but in the perpendicular plane. So the electric field and the magnetic field are perpendicular to each other all the time. And the changing electric field induces and propagates the magnetic field. And the changing magnetic field induces and propagates the electric field, and so it just continues on. And it turns out continues on at the speed of light, 3.0 times 10 to the 8th meters per second. Now we've got a couple expressions that I don't know how important these really are, but we've got the energy density of the electric field, the energy density of the magnetic field. And what Maxwell figured out is that the speed of light was equal to the ratio of the electric field to the magnetic field. And in this case, that ratio, if you go ahead and solve for the electric field here and the magnetic field here, is equal to 1 over the square root of a couple of constants. So the permittivity of free space and the permeability of free space, both of which are known at this point. Cool, and you plug them in, and this comes out, lo and behold, to 3.0 times 10 to the 8th meters per second. And again, Maxwell was actually able to calculate this before anybody even had an idea of what they were, that these lovely electromagnetic waves existed. Didn't even have a name yet when he figured out that they must have this electric field and magnetic field that are perpendicular to each other, that they propagate at the speed of light. Now, one thing that's different about these electromagnetic waves from some of the other waves we've studied is that these waves do not need a medium through which to travel. They can travel through a vacuum. Now, they can travel through a medium, but they don't need one. They can travel right through a vacuum, and so that's kind of unique. Every other wave we've studied at this point needed a medium through which to travel, whether it was a wave on a string or sound waves, things of this sort. If you go out in outer space and you yell, nobody can hear you because there's no air out in outer space, and sound needs a medium, air to travel with. Well, early on, every other wave we kind of have experience with needs a medium. So they kind of thought, well, maybe light does too. So maybe outer space is just filled with some substance, and we don't know what that substance is, so we're just going to call it the ether. And so they used to think that outer space was full of this mysterious substance called the ether. Well, we now know that's not true, but light does not need, and electromagnetic radiation in general does not need a medium through which to travel, and can travel through empty space. Now, you might have noticed that I've been interchanging the terms electromagnetic radiation and light, and for good reason. Now, when Maxwell originally postulated this presence of electromagnetic waves, and that they travel at 3.0 times 10 to the 8th meters per second, well, later on, somebody measured the speed of visible light at right around 3.0 times 10 to the 8th meters per second, and kind of the, bells went off in their head and said, oh, light must be an electromagnetic wave, a la, Maxwell. And they had actually discovered the presence of these electromagnetic waves that were not visible. And so what they figured out is that there's this entire spectrum of electromagnetic radiation, a very tiny portion of which is visible light that can be detected by the human eye. And the difference in these electromagnetic waves is frequency and wavelength. Now, all of them propagate at this speed of light, at least they do in a vacuum, and the speed in air is very similar. And we'll find out in the next chapter that the speed in other mediums slows down depending on the medium. But in vacuum, it's 3.0 times 10 to the 8th meters per second, and in air, it's almost essentially the exact same value, and we just end up using the same value. And we'll find out it slows down appreciably in, say, water or through glass and things of the sort, but we'll save that for the next chapter. So then electromagnetic radiation does have a characteristic wavelength and frequency, and there's a mathematical relationship to them that we've seen before. And so wavelength times the frequency is equal to the speed of a wave. And again, this was true for waves on a string or an ocean wave or things of the sort. It is also true for electromagnetic waves, including light. And so oftentimes when we say light in this context, we don't just mean visible light. It might mean infrared light and UV light. And the whole spectrum, as we'll see. And so again, you got to be careful. When we say light, most people in everyday life are talking about visible light. But in this case, light might be equated with just simply electromagnetic waves or electromagnetic radiation. All right, so simple equation here. C here is a constant as long as we're talking about light traveling through a vacuum or traveling through air. Got a lovely equation here that really only has two variables because C is a constant, that 3.0 times 10 to the 8th meters per second. And so if I give you the wave, you can calculate the frequency. If I give you the frequency, you can calculate the wavelength. And so these electromagnetic waves have all of the lovely characteristics of a lot of the other waves. You can set up interference patterns with them just like you can with other waves and stuff. But it turns out there's some unique things about light. And we'll learn about this a little bit later in talking about the particle wave duality of light. And so sometimes you look at light and it looks just like a wave as we expect it to, as Maxwell would have expected it to. But we'll find out that sometimes when you take a look at light, it looks more like a particle and has particle-like characteristics at the same time. And so we'll find out later on that light has both wave-like and particle-like characteristics. But in this chapter, we're focusing purely on the wave-like characteristics. So now let's take a brief look at the entire electromagnetic spectrum. We divide the entire electromagnetic spectrum into 7 different categories, and they differ based on frequency and wavelength. And keep in mind that from this lovely equation, if frequency times wavelength equals the speed of light, which is a constant, then they must be inversely proportional. As one goes up, the other one has to go down. And so we see here that frequency is going up as you go from radio waves up to gamma rays. Whereas wavelength is going up as you go from gamma rays to radio waves. And so radio waves having the longest wavelength, these can be meters long in wavelength and things of the sort, whereas gamma rays have ridiculously short wavelengths on the order of like, picometers or even femtometers. I don't know, they're really, really tiny wavelengths, but really, really high frequencies. And so there's that inverse relationship, and you should probably know the relative positions of these. If I say, which of the following has a higher frequency than ultraviolet, well, there's only two options. It'd either be X-rays or gamma rays. If I say which one has a longer wavelength than infrared, again, longer wavelength would be either microwaves or radio waves. So generally these have higher energy as well as you go up, and I shouldn't say generally, they do have higher energy as you go up. So energy, it turns out, is going to correlate with frequency, and we'll learn that in a later chapter, but you can kind of see how that plays out. So if you look at which of these is most harmful for you as a human, gamma rays. This is nuclear radiation. You get hit with a healthy dose of gamma rays and you're not long for this world. But notice X-rays aren't exactly good for you either. That's why the dentist, puts a lead thing over your chest when he's running an X-ray, and then he or she leaves the room, right? So, and they were probably not going to kill you like today or tomorrow, but they might eventually give you cancer. You definitely want to limit your exposure to X-rays. Now, if you're as pigment challenged as I am and you live in Arizona like I do, ultraviolet could get the best of you as well and also give you cancer. Maybe not quite as fast as X-ray exposure, but still cause you cancer. Then we've got visible light, and this really is just a narrow region of the spectrum. And we've got violet light kind of being the highest frequency, but the shortest wavelength, around 400 nanometer wavelength. So give or take. And then red being the longest wavelength, or the lowest frequency, and the wavelength being right around 700 nanometers, give or take. So just that really narrow range of the entire spectrum of electromagnetic radiation that human eyes can detect, that we can see. That's part of that visible spectrum. So if you notice, right above violet light in the visible spectrum is ultraviolet. Makes sense. And right below red light in the visible spectrum is infrared. So, and then finally microwaves and then radio waves. And notice infrared light is not going to cause you major problems. Now microwaves, it turns out, so they will cause you problems. Obviously, you don't want to hop in a microwave and nuke yourself, right? So, but it's not because they're so high in energy. It turns out they just make water molecules spin. And that causes a lot of heat to be produced and things of the sort. And unfortunately, we're full of a lot of water. And if you put something in your microwave that has no water content, it may not actually heat up. So, but all your food has water content, which is why they make good heating utensils. So it's the one that kind of falls out of line here, because radio waves, they're passing through me and you right now from the radio towers of whatever town or city or even out in the countryside where you live. There's radio waves passing through your body right now. So no problem. And infrared, not so much. Microwaves will cause you problems, but it's not because they're so high in energy. It's just because they have just the right frequency to make water molecules spin. Now, the last two topics we're going to take a look at, we encountered before in this course, and we encountered them in the context of sound. And sound propagates as a longitudinal wave, but still is a wave. And so electromagnetic radiation, which propagates as a transverse wave, is still going to follow both of these. And the first was the relationship between intensity and power for a spherical wave, one that spreads out in all directions, and we can kind of look at its intensity being spread out over the entire surface area of a sphere. And so intensity is equal to power over the area over which it's spread out. And if it's a spherical wave, that area is the surface area of a sphere, 4 pi r squared. And the big thing we probably took away with sound, and we want to take away here with light as well, is that the intensity is inversely proportional to the distance squared. And so if you're on a planet that's 10 times further away from a star, that star should appear dimmer. We kind of intuitively realize that. The farther you are away from a light source, the dimmer it appears. But if you're 10 times further away, it doesn't appear 10 times dimmer. It actually is going to appear 100 times dimmer, 10 squared times dimmer. So that's kind of the relationship we want to kind of establish. The intensity is inversely proportional, not to the distance, but to the distance of separation squared. All right, and then finally we've got the Doppler effect here. And so a little bit different version of the equation than what we saw. And this is actually an approximation, a pretty good approximation in most cases, but an approximation. And the idea that, in looking at kind of the velocity of the observer and the velocity of the source, this gets a little bit tricky because we're typically looking at this in the context of electromagnetic radiation of light with celestial bodies, planets and stars and things of the sort. And if we say, well, the Earth is still, and this other star is moving towards the Earth or something like this, things get a little bit funky because in the grander scheme of the universe, everything's moving. And the only thing we really know is what that relative velocity is. We don't really have like a stationary reference frame that everything's being compared to. And so the version of this equation we use is then this one where U represents that relative velocity between the two celestial bodies, the two objects in this case. And most of the time you're going to see it's Earth and then some other star or planet that's either emitting or reflecting light in some way, shape, or form. Turns out this equation is only really great as long as the relative velocity between the two objects is much smaller than the speed of light. Once it starts actually approaching the speed of light, relativistic effects become a problem, and this equation is not so accurate. So, and the closer that becomes to the speed of light, the less accurate this equation becomes. So that's a place where we wouldn't use this approximation. All right, so in this case, not a lot of calculations in this chapter, but we will go ahead and do 3 representative calculations. And the first one says the wavelength of a violet photon is 400 nanometers. What is the frequency? Now, the truth is I meant to put 2 sig figs here, and I realized 400 only has 1 sig fig, so maybe I make this 4.0 times 10 to the 2 nanometers, but I did want to put it in nanometers, and usually, so for something in the visible region of the spectrum, going to be quite commonly expressed in nanometers rather than meters. All right, the question is, what's the frequency? Well, again, there's an inverse relationship between wavelength and frequency since the product of the two is just equal to a constant, the speed of light. And so you rearrange this and solve for frequency, you just get the speed of light over the wavelength. It seems straightforward enough. Speed of light is 3.0 times 10 to the 8th meters per second. And the key is this: if you just plug in this wavelength in nanometers, you're going to run into a problem. So what units, I want you to think about, should the frequency actually have? Well, frequencies come out in hertz. Well, what's a hertz? Well, a hertz is equal to a 1 over seconds, or inverse seconds. And so that's the units I need to come out with, which means that meters needs to cancel. And so if you're using this value for the speed of light, which you almost guaranteed you are, then your wavelength better be put into this equation in meters. If you don't have it in meters, you need to convert. Well, 400 nanometers is 400 times 10 to the negative 9 meters. So if you take that 400 nanometers, if you want to see the conversion written out here, we'll put nanometers on the bottom, meters on top, and 1 nanometer is 10 to the negative 9 meters. So 400 times 10 to the negative 9, that's kind of where that came from. So, but here those meters are going to cancel, and you're just left with inverse seconds or hertz for the units here. And so in this case, you can probably do this in your head. So if you really push came to shove, but we'll let our calculator do the heavy lifting. And so in this case, we got 3 times 10 to the 8th divided by 400 times 10 to the negative 9. Now, one thing to note: if you put this in your calculator and use your E button and you put 400, and instead of times 10 to the minus 9, you put 400 e to the negative 9, it just treats this as one number, and you don't actually have to put it in parentheses. But if you actually put in 400 times 10 caret negative 9, it's going to treat these as 2 separate numbers, and it will multiply by 400. I'm sorry, it will divide by the 400 and then multiply the whole answer by 10 to the negative 9. And so what you need to do in that case, if you plug it in that way, is put the whole thing in parentheses on the bottom there, or you'll get the wrong answer. And so we're going to get 7.5 times 10 to the 14th. And again, that's seconds to the minus 1, or hertz, as the case may be. Okay, second question. If the intensity of light from a star reaching a planet is 1800 watts per meter squared, what would be the intensity reaching a planet 3 times further away from the same star? Okay. Now we can set up a calculation for this, and it would be a little bit of a pain in the butt, but we could totally do it. The numbers aren't terrible and stuff. But if you realize this relationship, you're golden. And so if this case, if we're 3 times further away, then what should happen to the intensity? Well, the intensity should only be 1 over 3 squared as much, 1/9 as much. Well, if the original intensity is 1800 watts per meter squared, what's 9 times less than that, or 1/9 of that value? Well, that's just going to be 200 watts per meter squared. And if you understand that relationship, the calculation becomes pretty simple. Now, how would you approach this otherwise? Well, take a look here. The intensity changes, so the surface area of the sphere is changing. What's not changing is the power from the original star emitting this light, let's say if it's from a star. And that's what's not changing. And so if you rearrange this, you can see that power equals the intensity times the surface area of the sphere in this case. And so you can kind of go through, and in fact, let's just put that in as 4 pi r squared. And so in this case, power equals power. And so I1 times 4 pi r1 squared equals I2 times 4 pi r2 squared. The 4 pi's are going to cancel, but I1 was your 1800 watts per meter squared. R1, I'm going to leave it as R1, but I'm going to substitute in for R2 3 times R1 since it's 3 times further away. And by the time you square that, that's where that 9 is going to come from. And lo and behold, if you follow this out, it's a little more work, but I2 will still come out to 200 watts per meter squared. All right, finally, our last one here. If a star and the Earth are moving away from each other with a relative velocity of 3.0 times 10 to the 6th meters per second, by what percentage will the observed frequency of light be different than the actual emitted frequency? And will it be an increase or a decrease? Now, we can answer that last part of it right off the bat. Will it be an increase or a decrease? Well, again, if this star and the Earth are relatively moving away from each other, then the observed frequency should be down. And again, if you remember that race car coming around the track and you're seated right on the side and you hear this, and as it's coming towards you, the pitch is higher and the observed frequency is higher than the actual emitted frequency. But after it goes past you and is moving away from you, so then the observed frequency is lower than the actual emitted frequency. And same thing here, if the Earth and this star are moving away from each other, then the observed frequency is going to be a decrease as compared to the actual emitted frequency from the source. All right, we'll make sure we need to use the plus or minus sign accordingly to reflect that, as we'll see. All right, so in this case, velocity relative to each other is 3.0 times 10 to the 6th meters per second. We know the speed of light is 3.0 times 10 to the 8th meters per second. We'll set that up. So frequency observed is equal to the frequency of the source times 1, and then 3.0 times 10 to the 6th meters per second, all over 3.0 times 10 to the 8th meters per second. In this case, is it plus or minus? Well, in this case, again, I need, since they're moving apart, my observed frequency should be smaller, which means this here should be a number less than 1. It's only going to end up less than 1 if we subtract. And so that's ultimately kind of the guys here. So this plus or minus, if the two celestial bodies are moving towards each other, then you add, because the observed frequency will end up higher than the source frequency. So if they're moving away from each other, though, then you're going to subtract, as we're doing in this case. And so if we rearrange this just a little bit, so I'm going to say frequency observed over the frequency of a source, divide it by right through, and we're going to have 1 minus, and this is going to come out to 0.01 in this case. This is just 1% of that number, and because it's the velocity, the relative velocity is 1% of the speed of light, that's why the frequency observed is going to be 1% different than the actual emitted frequency from the source. And so in this case, this comes out to frequency observed relative to the frequency of the source is equal to 0.99, which represents that 1% change. Cool, and that's it. Like I said, not a ton of calculations associated with this lesson, but 3 kind of representative examples. If you have found this lesson helpful, consider giving it a like. Happy studying.